Okay, our next lesson is on the functional group called alcohols, and the ethers lesson will be in another screencast. Okay, so up to this point, all of our chemicals that we've been dealing with have been hydrocarbons, meaning that they all contain just hydrogen and carbon. And what we are doing now is we are introducing to you, or introducing into the molecule a different atom other than carbon and hydrogen, and that atom is oxygen. And we are going to add that oxygen connected to a hydrogen off of the alkyl group, and that's going to result in an alcohol. So one of the hydrogen atoms is replaced with an OH, a hydroxyl group, and that's what makes an alcohol. Okay. In this particular notation here for the general formula, R simply stands for an alkyl group. It could be a methyl group or an ethyl group. Essentially, it's a chain of carbon and hydrogens. And so when you see that symbol R, it represents the fact that we've got a bunch of carbon and hydrogens, a carbon-hydrogen chain like we've seen in the past. And what we've done to make it an alcohol is we've added this OH, the hydroxyl group. All right? And when it comes to naming alcohols, I've already showed you that we can call this a hydroxy, but if we consider the alcohol instead of a branch as being the main functional group, we give it the ending -all. So we've seen endings like -ane for single bonds and -ene for double bonds and -ine for a triple bond. Now if a molecule contains an OH, we will give it the ending -all. All right? Okay, naming alcohols. Again, I have a worksheet, and you can follow along. So let's zoom in here a little bit and take a look at the rules. Now, because the OH is now the functional group, the most important part of the molecule, the parent chain must contain the OH group. Just like when we were talking about alkenes, the double bond had to be in the chain. And same with naming alcohols. The OH will locate the main chain. So again, indicate the location of the OH group by using a number to identify which carbon the OH is bonded, all right? And that's just like when we use the number to locate the double bond, where we put the -ene. And because OH is the functional group, the OH will always get the lowest number, all right? So the OH will now be connected to the main chain. Name the branches as before. If there's more than one OH group, attach an appropriate prefix to the -all ending, so we can have diols and triols. And other than that, it's very straightforward, very similar to double bonds and triple bonds. All right. So let's take a look at some of these guys here. We'll take a look at this one first on the left-hand side. So just as normal, I need to locate that main chain. So if I'm looking at the main chain, I'll count here 1, 2, 3, 4, 5. That seems to be the main chain. I could count from this end 1, 2, 3, 4, 5. So it looks like it's 5 in that chain. And there is my OH group. That's going to determine the alcohol. That's going to determine the lowest number. So I have to number 1, 2, 3, 4, and in this case it doesn't matter which way, 5. So that makes this a 2-pent and then all right, or pentanol. So this is a 2-pentanol, all right? So we've named the main chain with the OH defining that chain and the OH getting the smallest number. Now our branches. Right there we've got our regular methyl group, and therefore this is in the 4th position. This is a 4-methyl-2-pentanol. All right? 4-methyl-2-pentanol. Okay, so let's clear the screen, clear the ink. We'll move things over a little bit here, and we'll try this one here. Okay, so let's take a look at this one. So there's our OH group here. Right there is the OH group, and that is our functional group. So it has to be on the chain. it may look like I have two methyl branches off of this, but one of them has to be in the chain. So let's see if we can find that chain. 1, 2, 3, 4, 5. Now you might think 6 here, but this is a propyl group, and it may be condensed, but we're going to assume that it's a nice straight chain of 3 carbons. So that's where our chain is going to go. So let's go with 1, 2, 3, 4, 5, and in this spot we've got 3 more, 6, 7, 8. There are 8 carbons in this chain with a branch here and a branch there and a branch there. And the OH is special. That's our functional group. It's not a branch. It is part of the main chain. So let's name the end part. Let's name the main chain. This is 8, so it's oct. It's got an OH on it, which means it's an octanol, and it's in the number 2 position. So this is a 2-octanol. All right? So you've got a 2-octanol. And we have here a chloral, and we've got a couple of methyls. All right? And again, alphabetical, chloral is going to go first. It's in the number 4 position. So this is a 4-chloro. And I've got 2 methyls in the 2 and the 5 position, 2, 5. Because I have 2 methyls, I need the prefix di, dimethyl, and then I need another dash to separate that. 4-chloro, 2,5-dimethyl, 2-octanol. All right? So let's clear and let's take a look at some drawing. All right? So again, drawing is easier. We've already seen drawing. Start with the N and work your way on from there. So I have a nonanol. That's very long, but let's do it anyway. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I have a 4-nonanol. 1, 2, 3, 4, which means I have an OH off of the 4th carbon. Now I've got a couple of ethyls off of the 5, 1, 2, 3, 4, 5, so I've got a C2H5, and here I've got a C2H5, and I've got 2 methyls, one in the number 2 position, CH3, and one in the number 3 position, CH3, and it doesn't matter whether they go up or down. Again, we can rotate around the single bond, and let's fill with H's. Remember, each carbon has to have 4 bonds to it, because there's 1 to this, there'll be 3 H's there, an H3, this one gets a single H, this one gets a single H, this one gets a single H, that one's full, H2, 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 and H3. Okay? So drawing is easier. Let's clear and we'll draw that next one. Okay, butane diol. Well, bute. 1, 2, 3, 4. And I have diol. That means I have 2 OHs. One in the 1 position, OH, and one in the 3 position, OH. And let's finish our H's. H2, H2, there's 3 bonds there, so a single H, and H3. All right? Okay, so that's how we name and draw alcohols. Okay, now I want to talk about isomers of alcohol. Remember, isomers have the same chemical formula but have different arrangements of their atoms. And we're going to have to talk about the different classifications of these isomers. Now, this is something different than what we've seen so far concerning organic chemicals. And the reason for this has to do with the location of the carbon, the location of the OH on what we call the key carbon. And this is going to become important in the near future when we talk about different chemical reactions that alcohols can undergo. And so the behavior, the chemical behavior of the alcohol as a chemical depends on where the OH is in the carbon chain. All right, and that's what we want to talk about right now. So primary alcohols indicated with a 1 and a degree sign. Sometimes they're called first degree alcohols, also known as primary alcohols. The way we distinguish a primary alcohol is to locate the OH and then to look at the carbon that it's bonded to. The carbon that the OH is bonded to is what we call the key carbon, and that again, like I said, is going to indicate kind of the way it's going to behave when we start talking about chemical reactions. And so if we look at the key carbon, and we notice that it has 2 hydrogens bonded to it, and that it has only bonded to 1 other carbon. So what we're looking for here is how many carbons is that carbon bonded to, and we see that it's bonded to only 1 carbon. That is what we call a primary alcohol. All right? Now the way I learned about primary alcohols didn't have to do with the key carbon, but it is a good way of knowing it. It has to do with where the OH is bonded in the carbon chain. You'll notice this OH is bonded at the end of the carbon chain, right at the very end. And so this carbon, the key carbon, is bonded to the O of the alcohol and to the C of the next carbon in the chain. And so you'll notice it's only bonded to 1 carbon, and hence it is a primary alcohol. All right? Let's take a look at secondary alcohols. So again, if we locate the OH, and then we locate the carbon that it is bonded to, the key carbon, all right? And we then take a look at how many carbons that key carbon is bonded to. You'll notice in this case, the key carbon is bonded to 1 and 2 carbons. So 2 carbons are bonded to the key carbon. That makes it a secondary alcohol or second degree alcohol. The way I learned it, instead of the OH being at the end of the chain, oops, didn't mean to write that, so we'll erase it. Instead of the OH being at the end of the chain, it is now actually bonded to a carbon that's in the middle of the chain. All right? So it's in the chain run and bonded to 2 others. Now a tertiary alcohol, again, we locate the OH group, and notice the key carbon is now not only bonded to 2, but bonded to 3 carbons. You'll notice it now has no H's, and so the key carbon is bonded here. The key carbon is bonded to 1, 2, 3 carbons, and it is therefore a tertiary alcohol. Okay? And the way I learned it was it's now at a junction for a branch. Instead of it just being in the line of the chain, it's at a junction for a branch. But looking at the key carbon is a very good way of understanding that. So, is 3-ethyl-2-pentanol a primary, secondary, or tertiary alcohol? Well, if we think it through, the 2 gives us the location of the ol. So that 2 tells me that the OH is in a number 2 position. My branch is in a number 3 position. So number 1, it's not at the end of the chain, or it would have a 1-pentanol, which means it's in line in the chain. And it's not in the position where a branch was. This would be 2-ethyl, 2-pentanol. And so it's not where a branch is, which means it's in the chain. That makes this a secondary alcohol. All right? So if we draw it up, 1, 2, 3, 4, 5, and let's not worry about these H's. It's a 2-pentanol. There's my OH. There's the 3. There's my CH3. You'll notice here that this guy is bonded to, the key carbon is bonded to 1, 2, therefore it is secondary. Okay? In order for this to be primary, I'd need my ol to be a 1. And in order for it to be tertiary, I need this to be anything but 1, but my branch has to be, my alkyl branch has to be the same number. All right. Polyols, we've already seen some examples of polyols. We named one, the diol. All right. So if I'm going to name this guy, this is an ethanol or an ethane, right? But it's got two ols. I could have the ol on this one. I could have two OHs on the same, so I do need numbers. This is a 1, 2 ethane diol. And this one here is 1, 2, 3. And this is propane triol. All right? Okay, so we can have multiple OHs on the same molecule. And we won't worry about those. We've got the names. Draw butane 1,3-diol. Now this is a slightly different notation than what we're used to. I usually put the numbers in front and then don't have a break, but this is also an acceptable way of doing it. So again, we can easily figure out what we're looking at here. We're looking at a butane, 1, 2, 3, 4. I'm going to have an alcohol on the 1 and on the 3, and the rest of them are going to be filled with H's. H2, H2, H, H3. Okay? Very straightforward. We can have cyclic alcohols. All right? So we can have, again, the cyclo. Here we've got an OH on it. There's no other branches. There's no double bonds. So this is cyclo, and it's H hexanol. This is cyclohexanol. No need for a number because there's only one OH, and that defines where it is. We can have aromatic alcohols, and again, we could have the benzene ring containing that. Now this has a special name. So this is our phenyl group. So this is phenol. All right? So this is phenol. Okay? Properties of alcohols. Alcohols are polar because of the OH, right? So if we've got that OH group on there, we have slightly negative, slightly positive, all right? So that makes it polar, which means their intermolecular forces are London and hydrogen bonding. So alcohols have a higher melting point and boiling point than their corresponding hydrocarbon, all right? And a good example of that is if we've got ethane, CH3, CH3, that is ethane. That is part of natural gas. We burn that in our Bunsen burners. And as soon as I change that CH3, CH2, and put an OH on that, that is ethanol, ethanol, and that is a liquid, that is ethane, and that is a gas. All right? So just the presence of that OH makes it sticky enough that it becomes a liquid. So alcohols are soluble in polar solvents, and again, the longer the carbon chain becomes, the less soluble the alcohol becomes in the polar solvents. And we talked about that in our last unit. If we have something with lots of carbons on it, then that non-polarness of that molecule becomes greater, and it is not as soluble in water. So how do we make alcohols? Well, alcohol, beverage alcohol, can be made through a fermentation process, but that's not what we're talking about here. We're talking about various types of chemical reactions that can take place, and we've already seen one. We can add water to an unsaturated hydrocarbon, and this is called an addition reaction. And so we've seen already before that we can have this acting as an HOH, right, a hydrogen hydroxide. That bond can break, and therefore one of them can get an H, and there is the H2, and then the other CH2 can get the OH on it, and then this becomes ethanol. All right? So if we start with ethene, because of the double bond, and we add the hydrogen and the hydroxide, well, it's not a hydroxide, but the hydrogen and then the hydroxyl group, then we end up with ethanol. All right? So we can do that by an addition reaction, and we've already seen that. Draw the structural diagrams and write the IUPAC names that represent the formation, the reaction that represents the formation of 2-methyl-2-butanol. Okay, so again, when you're given a question like this, one of these synthesis problems, always start with the product. Let's draw it out and see what we've got. 1, 2, 3, 4, 2-methyl, CH3, and 2-butanol. So there's my OH. And I've got an H3, nothing, H2, and H3. And we are going to be trying to produce this. And because we've only learned one reaction to produce the alcohol, it's going to be an addition reaction with water. So we're going to add this guy here. And what we need to do is we need to figure out where is the double bond going to be. Well, I can remove this H and remove this OH and put the double bond here. So I could have a CH2 with a double bond, then a C, CH3, and CH2, and CH3. And remember, we have to follow Markovnikov's rule for this, because I have to put the H on the carbon that has the most H's. And in that case, it's this carbon right here. So if I were to add the hydrogen to this carbon and the OH to this carbon, would I get the product that I desire? And yes, I would. There, that's become a 3, and that was a 2. And there's my OH. So I would get the correct product. That would be my major product. And so this chemical would work. What is this particular substance? 1, 2, 3, 4. It's a bute. It's got a double bond, so it's a butene. And it's got a methyl in the number 2 position. This is 2-methyl-1-butene. Okay? Now, you might ask, why can't we put the double bond on this side? And it turns out that we can. If the double bond was there, one of these H's would be gone. CH, CH3. This guy here would be a CH3 because he came from this spot. And this would have my CH3 up here. And if I were to add now my water to this, according to Markovnikov's rule, the H will go over here. And if it goes over here, it results in the same product. So we could have also used 2-methyl-2-butene. Both of them would result in the same major product. All right? So in this case, it didn't matter which of the 2 possible hydrocarbons that we used. Combustion reactions, well, we all know that hydrocarbons burn, alcohols burn as well. 1-propanol, C, 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 OH, H2, H2, H3. And if I'm combusting, I put it all together. C3, 2, 4, 5, 8, H8O plus O2, CO2, H2O. 3 carbons, 3 carbon dioxides, 8 hydrogens, 4 waters. 3, 4, 5, 5 O2s. All right, standard balance. So alcohols can burn. Alcohols can also undergo what is called an elimination reaction. So they can decompose to produce an alkene and water. This is called a dehydration reaction because water is eliminated from the alcohol and this reaction is catalyzed by sulfuric acid. Sulfuric acid absolutely loves water. When I make a sulfuric acid solution from concentrated sulfuric acid and I add that concentrated sulfuric acid to the water, it gets super hot. And that's because it's giving off energy, and that energy is coming from this strong attraction that sulfuric acid has with water molecules. So if you want to rip a water off of a molecule, use concentrated sulfuric acid, all right? So 2-propanol, if I use some concentrated H2SO4, all right, I'm going to rip off a water molecule, and it's going to leave me with an alkene, because what I'm doing now is the opposite to an addition reaction. I'm ripping the water off. It's actually going to produce, what's it going to produce here? It's going to produce, and this is going to be propene, all right? Okay? And it's going to look like this. C, 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 OH, H3, H, H3. The concentrated sulfuric acid as a catalyst, that's why I write it above. That's going to rip off a water, and that is going to come from here, and it's going to come from one of these guys. Or one of these guys, doesn't matter. In this case, it makes no difference. When you do that, you end up with now CH2, because one of the H's have been removed with this, a double bond, which is formed between this bond and the H bond being broken, and then a CH and a CH3. Okay? So 2-propanol becomes propene. And that's an elimination reaction. It's a special type of elimination reaction that it's called a dehydration reaction, because we're ripping off water. Write a balanced structural formula for the dehydration of 2-butanol. Write the names of the products formed. So 1, 2, 3, 4. And I have the OH right there, OH, and I have H3, H, H2, H3. All right? And we're going to dehydrate it. So we want to do the dehydration reaction. I need H2SO4 to remove the water molecules. And that's going to leave me a water, just one water molecule. And that can come off of here, or it can come off of here. All right, so I'm actually going to get 2 products, 2 possible products. If it comes off the first one, that one has to drop by 1, CH2. The double bond has been formed. The H is still there because it's the OH and that guy that come off. CH2, CH3, and so that is a 1-butene. Or it can come off of this guy here. This H can be removed. H2O, CH3, CH, and now this guy has the double bond right there. We needed to remove one of those H's. CH and CH3, all right? And this is 2-butene, all right? There would actually be geometric isomers for this, so you might get some cis-2-butene and some trans-2-butene, and one would be more than the other, but you don't have to worry about that stuff here, okay? All right. And there is some questions, but I don't know whether that's the new textbook or the old textbook.